Dear students, welcome to this Friday lecture. Today's going to be about NVIDIA's CUDA API that can be used to write GPGPU programs. And first off, we're going to start with a little overview of the CUDA API and its internal workings. So, NVIDIA's CUDA actually consists of two APIs. One API for the host or for the CPU, and another API for the device or for the GPU. And on the device side, the CUDA API is centered around something that is called the kernel. And at first sight, the kernel is basically just an ordinary C or C++ function, but only for this peculiar keyword global here, which makes the C function a kernel. And the kernel itself contains ordinary C or C++ code, but for certain language constructs, such as, for instance, recursion or certain other object-oriented language features from C++ that just cannot be used with the device-side API. But nevertheless, what's inside the kernel is pretty much C or C++. But the execution mode is different. Like, the execution mode is that the kernel is an entry point, very much like the function main is on the CPU, but only that the entry point is not executed by only a single thread, but by a bunch of threads at once. And then we have a host API, and the host API is responsible for different things. Like, it is, for instance, responsible for data transfers. And in fact, when data transfers are initiated, the host is actually responsible for both directions. Like when we discussed in the architectural sessions that GPU execution models are pretty much one-way streets. This actually also manifests here in that whenever there is any communication with the device, then the communication is initiated by the host, and there's only very little communication back from the device that is initiated by the device, actually. So, and the host API is also responsible for kernel invocations, so it will make sure that those kernels are actually called. And then there is also other control flow that we'll also talk about in this session that is associated with CUDA programs and where the host is responsible for calling certain API functions. So, and on the host side, the API is really just an ordinary C or C++ API, and there are also language bindings for other languages. So on the device side, we have those kernel functions, and of course we can only have one kernel functions, but we can have a bunch of kernel functions. So our CUDA program would basically be comprised of a bunch of kernels that operate on the device side and that are executed by multiple threads at once. And then we have the C or C++ host side API that calls those kernels on the device and initiates kernel invocation. And that is responsible for transferring data so that the kernels can process that data on the device. So CUDA is a C and C++ language extension for GPGPU computing on NVIDIA GPUs. And there are also other GPGPU programming languages, such as OpenCL or Vulkan, for example. And in this lecture, we're mostly focusing on NVIDIA's CUDA because programming with CUDA is actually a bit more simple than programming with OpenCL or with Vulkan, where you, in order to achieve the same thing, have to write many more lines of codes and have to take care of much more boilerplate than you actually have to do with NVIDIA's CUDA. Like, in this sense, NVIDIA's CUDA is actually much more focused on being a streamlined API that is in line with typical C APIs, where you have dedicated functions for data movement and abstracts certain things from the developer that OpenCL and Vulkan actually expose in a very verbose way. Nevertheless, when it comes to understanding the paradigms behind GPGPU, it will generally suffice for us to learn NVIDIA's CUDA, and with that we will also understand conceptually how APIs such as OpenCL or as Vulkan's compute shaders or OpenGL's compute shaders would work. And the CUDA APIs and the GPGPU APIs in general basically map the stream processing model from the last session to GPU architectures. And in that sense, kernels are basically the substitute for the compute commands. And then in the stream processing model, we had FIFOs. And the FIFOs are basically what on the GPU is the asynchronous host interface. In particular, we will focus on CUDA because CUDA implements a so-called single source paradigm. That means that we have a single code base where code is shared between the host and between the device. And in order to tell the compiler and the runtime and the overall CUDA toolchain that functions run on either the host or on the device, we just use certain keywords that allow us to annotate functions or that allow us to annotate member functions, for instance. CUDA comes with a dedicated compiler toolchain, in particular with the NVCC compiler. And the NVCC compiler will run over our CUDA code, and the CUDA code goes usually into files that have the ending CU. And by that, the compiler can identify that this is a file containing CUDA code, and the CU files or the CUDA files can contain both host code and device code. And the NVCC compiler and the toolchain will be able to figure out which parts of the code are meant for execution on the host and which parts are meant for execution on the device. And in particular, this is implemented by means of those annotations. And then it will split those parts of the code, and it will compile the device code into something that is called SASS, which is the assembly or machine code of the GPU. And you can also, there's an intermediate representation that is called PTX that can be inspected and that can be optimized. And that is also an intermediate representation that the code can be compiled into. So we have this one tool chain that processes device code. And in the same CUDA files, in the same CU files, we can also use host code and we can use the host APIs. And the NVCC compiler will figure that out, and it will take that code and will pass it over to the host compiler, like GCC or CLang or whichever host compiler you're using on your system. And the host code is basically responsible for allocating things and for managing resources and basically for implementing the interactive host interface and all the communication that goes over the host interface. And the device code implements the logic that runs on the GPU. And for the device side, we have a subset of C and C++ that can be used in those kernel functions, and they are basically a language extension. There are certain keywords that come on top of C++, like for instance the global keyword and the device and host keywords that we already saw. So those are extensions. And on the host side, the code is, with very little exceptions, is pretty much ordinary C or C++ code. And we have just certain API functions, and those API functions are usually prefixed with the string CUDA. And that tells us that this is a CUDA API function. And nevertheless, those are just simple API functions that are used, but the language is really just C or C++. And the code that is generated for the host is actually passed to the host compiler for processing. And in general, on the host, we have a program that is run with the same execution mode that a CPU program is run in, however many threads we allocate on the host is how many threads we also later have in our program. And the device code in general is defined in a way where a kernel is executed by many threads at once. As a matter of fact, there are actually two APIs that can be used on the host. There's the so-called driver API, and then there's the runtime API. And the driver API is really just an ordinary C or C++ API. And the driver API is a bit more low level and gives control over certain things. With the driver API, for instance, we have a context object, and we can manipulate that context object, and we can control when that context object is created. And we're also responsible for compiling device code. With the driver API, the device code can be compiled in a just-in-time fashion. And the runtime API is actually a bit more abstract in that device code compilation is not in the hands of the user in a sense that this happens at runtime and is performed using API functions. And the runtime API is actually quite a bit more streamlined and hides certain things. For instance, there are context objects with the runtime API, but the developer actually never sees those context objects. Like for instance, when with the driver API, we would create a context object, the runtime API would just see us call certain functions, like would see us call, for instance, CUDA malloc or CUDA memcopy, and those functions are responsible for memory movement and for data transfers. And the runtime API will recognize whenever there's the first call to one of those functions that a context object will be created, and then under the hood will create a context object for us. But there's never any reason for us to interact with that context object. So the runtime API is much more streamlined, but in general, there's usually not a big difference between the two APIs when it comes to performance. Like you would usually only use the driver API when you need control over certain things that the runtime API just doesn't give you control over. And for those reasons, we will in this lecture focus on the runtime API because it's just much more simple. And as a matter of fact, this is also like the default API that is used by people. Like when people write a CUDA program and they're not sure about which of the two APIs to use, like the driver API or the runtime API, they will usually choose the runtime API, and this is basically the default way of programming CUDA programs, and this is also what we will stick with in this lecture. And in particular for the runtime API, but also for the driver API, you will find very thorough documentation, and the documentation is available in the form of the CUDA Toolkit Programming Guide. And in fact, many of the examples that I'm presenting here in this lecture are directly taken from the programming guide, like the examples that we discuss when we talk about shared memory. So it is very easy to comprehend those examples via the programming guide, and the programming guide is available on NVIDIA's website. So you can search for the CUDA Toolkit Programming Guide on the NVIDIA website, and then you will find the programming guide, and you will find that this provides very thorough documentation for all the CUDA functions, and that it has very in-depth discussions and many examples that help you to very thoroughly understand NVIDIA's CUDA. And as a matter of fact, when you install NVIDIA's CUDA on your machine, you can also, like, optionally install the samples with the CUDA toolkit, and I advise you to do so when you install NVIDIA's CUDA. I advise you to also install the samples, and the samples also provide very much insight into how CUDA can be programmed. So CUDA has been around since around 2009 and was originally introduced with the G80 chipset, that is with the GeForce GTX 8800. As a matter of fact, this chipset is actually not supported by newer CUDA versions anymore, and CUDA categorizes its devices by their so-called compute capability. Each device is assigned a compute capability, which is basically a number where higher is better. Like, for instance, the Fermi GPUs, like the GTX 480 and the 580, they had the compute capability 2.0. And compute capability 2.0 was just associated with certain features that were supported by the GPU, so that could be used in the CUDA programs. And then there are compile time macros that can be used to ask the device for its compute capability, and there are also runtime functions that can be used to query the compute capability at runtime. And the compute capability can be used to determine if certain features are available on the GPU architecture that is targeted. And this is a mechanism that is similar to the extension mechanism by OpenGL, only that CUDA is not a API that is developed by a consortium, but is an API that is developed by a single vendor. So the mechanism of determining which GPU supports which features, and if those features can be accessed via the API, this mechanism is much more simple than the extension mechanism provided by OpenGL. So the basic execution model of a CUDA program, and this is what I already indicated, is that we have like a thread on the CPU, and that thread on the CPU is concerned with calling CUDA kernels, and those CUDA kernels are executed by many threads at once, and then we have the execution returning to the CPU, and the CPU will execute more CPU control flow, like for instance memory transfers or other control flow, and then we'll call the next kernel, and then the execution is returned to the CPU, and then the kernel will be executed, and so on. And then in between, the CPU will perform data transfers, and those data transfers are done using DMA. Like, this is handled by the graphics card's driver and by the CUDA runtime. And in particular, there are several calls, like for instance kernel calls and also memory transfer calls, that are allowed to overlap and that are asynchronous, where basically the asynchronous host interface of the GPU is used. Like, we will learn in particular which of those functions are run asynchronously and how we can make those functions actually run asynchronously and how we can define interdependencies between those functions. Like, for instance, if you initiate a DMA memory transfer and then call a kernel, it is important that the behavior is known as of when the data is available and the kernel can use it. And in general, we have this execution model where the CPU runs one or multiple threads, and each of those threads is responsible for calling multiple GPU kernels. So in the CUDA GPU, execution model is data-centric. That is, when we create threads with the CUDA API and those threads execute kernels, we do so implicitly by defining a uniform grid. That is, the user or developer defines a uniform grid and tells the CUDA runtime to execute that grid, and then the CUDA runtime will allocate thread resources for each of the cells inside that grid. And then the user is usually required to map those threads to their data. Let's just imagine we're processing a one-dimensional array, like the one-dimensional array here, where the first index is 0 and the last index is n-1. And then the user would just divide that data array into a uniform grid of blocks, as I'm indicating here. So the user defines that grid of blocks, and the CUDA runtime will allocate threads for each of the blocks. And then later, inside the kernels, we identified which thread we are and which block we are in, and by that we can access the individual data items in the data array. Like in the case here, we would have 1 to 3 blocks that process this array, and inside each block we have a bunch of threads that are executing. Like here we would have 4 threads per block that are executing, and each of those threads has an individual index. Like, we can identify each thread by its zero-based index, but we can also identify the blocks by their index. Like, this here is the block with index 0, and each of the blocks also has a uniform dimension. That is, the dimension is the same for each of the blocks. In the particular case, the block dimension, like the block size, is 4. And then we would identify each individual block and each individual thread inside that block. Like, each block would have a index 0 and 1 and 2 because they're 0-based. And then we're also able to identify each block by its individual index. And that allows us to compute global indices, and those global indices allow us to compute indices into the data array. Like, a global index that we would compute from here would be the block index times the block dimension plus the local thread index. And that would basically give us the global thread index, which would also be the index that we use to access those data arrays. Like, in the particular case, if we are the thread with index 1 and block index 0, like, we would compute the data item that this thread is responsible for by multiplying its block index by the block dimension and then adding the thread index. Like, we can, of course, also have one thread being responsible for multiple data items, but this is the basic way that CUDA uses to map threads to data items. And there's the one-dimensional case. And as a matter of fact, those block index and thread index and block dim, they're actually, they're like keywords, or they're like built-in variables. So those are keywords that are available on the device. That is, whenever you execute code on the device, you have access to those keywords. Like, as a matter of fact, those variables are also actually three-dimensional vectors, so you would access them via their member variables x, y, and z. So this is a implementation detail, but those are basically like part of the CUDA device-side language extension that you can use. So, and CUDA allows us to perform those mappings in both 1D and also in 2D. Like in 2D, we would have like those blocks being two-dimensional blocks or tiles, and each of these tiles would have like a number of different threads, and each of the blocks would also have an index, and those indices would again allow us to compute global indices for each of the two dimensions, like for the x and for the y dimensions. And we would again do so by using the block index and block dimension and thread index variables that are built-in variables with the CUDA device-side language. And then in 3D, we will have a very similar mapping that I just won't show here for simplicity. So here's actually a bunch of examples of how we would take a given data domain and allocate threads, that is, enough threads so that they're able to process that given data domain. Like in 1D, we might imagine, for example, that we sort n numbers, and then we would take those n numbers and would subdivide the array with those n numbers into blocks, and in 1D, those would just be stripes. And each block would have the size b, and that would give us the grid size, which would be n over b. And like, we would usually not have the number of items that we're processing exactly divisible by the block size. So in order to determine the grid size, so the number of blocks, we would take n over b and would round it up, and that would give us the number of blocks, that is the grid size. So and in 2D, the typical example would be an image that we render, and that has this size w times h pixels. And then we subdivide that image into tiles. Like our blocks are now 2D blocks of size bx times by. And then that would give us the grid size of gx, where we would divide the width of the image by the block size in the x dimension. Then we would again round that up so that we have enough blocks also for the overlap. That is where we have, like, at the boundary a couple more pixels that are the remainder of the division. And we would do the same thing in the y dimension. And the typical example for 3D would, for instance, be like that we would process a CT image, which is basically like a 3D image where we have a bunch of images that are stacked up. And then we would do the same computation, but only in 3D, and where they would actually be three-dimensional blocks. So here is basically the same image that I showed you earlier for the two-dimensional case, where you can see the indexing scheme once again. Like, we have a indexing scheme where we have two-dimensional block indices. Like, this here is the block 0, 0. This is the block 1, 0. And in the second row, we would again have a x index of 0, 1, and 2, but the row index would be 1 here, like where the column index would be 0, 1, and 2, and the row index would be 1. And then inside each block, we would again have thread indices, and those thread indices would also be 2D. Like, we would have those T00, T10, indicating in which row and in which column we currently are. So, and here I'm illustrating how one would just set up that grid from the slide before with CUDA code. And imagine we would just have this kernel here, like indicated by this identifier global, and other than that, it's just a simple C function. And it's a C function that is executed on the device, and we would have to call the kernel from our host code. And for that, we use this peculiar notation here that I'm going to elaborate on in a little bit. Like, we can mostly ignore it for now. Suffice it to say that it is the way to call kernels with the runtime API. And it is, like when I said that the runtime API is mostly C and C++, then this is actually the only exception where the runtime API provides us with a language extension, which is in the way that kernels are called. Like, it's really a very simple language extension, actually. And we call that kernel by calling the function func here. Like, this is the name of our kernel function. And then we have these three brackets, and then we define the size of the grid. Like, we define the number of blocks, which I indicate by the acronym grid size here. And the size here is 3 columns and 2 rows. And then I'm also specifying that we have blocks of size 2 by 2. And then I'm passing that to the CUDA function call. Like, I'm first specifying the grid size, and then I'm specifying the block size, and then I'm calling the CUDA kernel like this from the host. And then when the kernel is executed on the device, the aforementioned built-in variables are filled. Like, there will be a kernel execution where the thread index x is either 0 or 1. And the same is true for y, because we have 2 by 2 blocks. And then there is a kernel execution, like for each of those, we would have the block index x being either 0, 1, or 2, because we have the x dimension being 3, like we have 3 columns. And we would have kernel executions where the block index in the y dimension is either 0 or 1, because our grid size is 2. And then we would also have the block dimensions available, like the blockdim x variable and the blockdim y variable here, and the two of them would be 2 because the block size that we specified was 2. So basically, by specifying the grid size, and we would actually also have to perform the rounding on our own, then we would pass the grid size and the block size to the kernel call configuration. And then inside the kernel, we would have those built-in variables available that we can access and query which thread we actually are. So, and I actually hope that the drawing that I showed you of this grid of 3 by 2 blocks, like the two-dimensional grid from the slide before, I hope that it seemed a bit familiar to you guys, because as a matter of fact, the design of the shader multiprocessors that we discussed in the architecture part of the lecture is actually quite similar. So those shader multiprocessors that were concerned with processing fragments or vertices, they're actually also very similar to our grids in that they are subdivided into multiple cores. Like, our shader multiprocessor will consist of n cores, and then we have our compute grid, which consists of m blocks. So our GPGPU program, our CUDA program, will now execute those m blocks on the n cores of the shader multiprocessor or of the shader multiprocessors. And the functional unit that is concerned with doing so, or with planning how this is done, is the warp scheduler. And the interesting question is now, like, what we will in general see is that n, the number of cores, doesn't equal m, the number of blocks. So if the number of blocks m is much smaller than the number of cores, for instance, then we will see that our GPU is underutilized. So most of the cores will actually idle, and we don't use the GPU to its full extent, and for that reason we cannot utilize the full capacity of the GPU, and therefore the GPU will not operate at its full efficiency. So at the same time, if there are many more blocks than there are cores, then we would have to serialize the workload so that a number of blocks is executed sequentially. So the size of the problem and the way that we subdivide our computational domain using the grid metaphor determines how efficient our program actually runs. Because the user is pretty much free to determine the size of the blocks and of the grid that is actually used. And there are a number of performance metrics that we will later discuss that we can use to determine what the optimal size of our compute grid is using a static code analysis. And then we will try to find the best configuration so that the warp scheduler is able to, as efficiently as possible, schedule the computational workload that we process using the GPU. And so in general, it is important that we provide enough work for the GPU scheduler so that the application doesn't starve. And at the same time, we have to make sure that blocks aren't sequentialized. And the very way that blocks are later distributed to cores, like with our n cores and with our m blocks, And the very way that the workload is distributed to the actual cores is determined by the runtime scheduler, like the warp scheduler. And this is very opaque. Like, we don't actually know how this distribution is performed, and like there's potentially also load balancing happening where the warp scheduler determines which blocks at which time should be scheduled on which cores. But this is pretty much opaque, and we have only very little means available to influence that, and we will discuss those means in a little bit. But it's actually not like documented how the runtime scheduler performs the actual load balancing and distribution of the workload to the individual compute cores. So, and the execution model when it comes to compute workloads is actually the very same that we also discussed in the context of vertex and of fragment processing. So as a reminder, in the context of vertex or fragment processing, we had the warp scheduler, and the warp scheduler would schedule thread groups, and those thread groups are called warps, and they would like contain 16 or 32 or 64, depending on the architecture, threads. And those threads would appear to execute their instructions in lockstep. And then the warp scheduler would schedule like a bunch of instructions to each warp, like maybe 4 or 8, like a handful of instructions to the warp. That would allow the warp scheduler to perform latency hiding. That is, whenever a warp would perform an instruction that has relatively high latency, like a memory access, for example, they would make the whole warp idle on that processor and would store its state in registers. So basically perform a context switch. And we also learned that the context switches are quite lightweight, in that the warp scheduler would basically just keep all the state around in the registers where the state was in the first place. So, and then the warp scheduler would just schedule another warp and on that shader core. And the very same mechanism is actually also used when it comes to compute workloads. So you can already see that the granularity of the warp is a bit different than the granularity of an actual block. So on the one hand, the spatial dimension is different. So the block size in general doesn't equal the warp size. And in particular, like usually warps are actually a bit bigger than typical warps. Like this is actually pretty much application dependent and hard to say for each and every application what the best block size would be. Like there are a bunch of factors that this depends on that we will also discuss. But typical block sizes might, for instance, be on the order of 16 by 16 or 32 by 32 when it comes to tiles, so when it comes to 2D workloads, which is actually quite a lot more than the actual number of threads per block. So the granularity is different in the spatial dimensions, and the granularity is actually also different when it comes to instructions, because the warp scheduler would not like schedule all the instructions from the block to a warp, but would only schedule a handful of instructions at a time. So, and other than that, the execution model is actually quite similar to SIMD, and like we already discussed all that, but basically the execution model is quite susceptible to dynamic branching. So as soon as there are branches, then threads have to wait for each other, like threads that are in a warp when the whole warp executes a branch, and like there are like 1 or 2 threads that don't take that branch, then they actually have to wait. So all this is very similar to what we also discussed in the context of vertex or fragment processing. And like here's actually the very same diagram again. Like we have our GPU program, like our compute workload, and the compute workload is subdivided into blocks by the user, and the blocks are assigned or are subdivided into threads. So this is basically the grid that we discussed. And then we have the runtime scheduler, and the runtime scheduler would schedule the blocks on the shader cores, and the granularity here would be the warp. And the very same type of processing that was valid in the context of rendering and of the rasterization pipeline is now also used in the context of compute workloads. So the next thing that we should discuss is the NVIDIA GPU's memory model, which is exposed by the CUDA API, and which is actually quite a bit more heterogeneous than the typical processor's memory model, like when you compare the memory model to that of a CPU. And the slide here gives a brief overview of the various types of memory that are exposed by the CUDA programming model and that we can use via the CUDA API. And the first and probably also the most notable type of memory is the so-called shared memory. And shared memory can be thought of as a small L1 cache that can actually be addressed directly from within the device code. And threads and words that are executed on a shared memory, they can access shared memory. And synchronization is required whenever we access shared memory, when multiple threads access shared memory from within the compute kernel. And the size of the shared memory depends on the architecture and is usually like around 16 kilobytes or 64 kilobytes. And as a matter of fact, the shared memory is actually so much similar to L1 that usually there is a L1, like a non-addressable L1 of the same size located directly next to the memory region where the shared memory goes. And with newer CUDA versions, it is actually possible to devote the shared memory to become an L1 cache, or vice versa, to make part of the L1 shared, so that you basically can decide if you devote all the L1 memory to that addressable memory region, or if you allow the cache control system to make use of all the memory. There are dedicated API functions for that. Then there's so-called global memory, which essentially is just DDR memory. And the DDR memory is cached on some architectures, like there's usually a L2 cache between the DDR memory and between the shading multiprocessors. Like, it's not a necessity, like there were architectures that actually weren't cached. And then each thread also has a limited number of registers available. And those registers can be used to store the local state of each thread. And at some point, we might run out of registers, so the state does no longer fit into registers, and then the CUDA runtime will spill the state into so-called local memory, which is yet another memory region. And essentially, local memory is just DDR3. So this is just basically another name for DDR3, where register content is spilled to. And then there are other special purpose memory types, like, for instance, the so-called constant memory. Like, there's a tiny bit of constant memory that is available to the shading multiprocessors, and in order to make use of constant memory, we have to allocate a memory region by using the keyword constant. And then there is also texture memory. Like, texture memory is cached, and texture memory is optimized for fast read access and actually cannot be addressed directly from within the device code, but can only access using accessors. So when it comes to a hierarchical view of the memory system, then we have, on the one hand, we have threads, and the memory granularity on that level is the per thread local memory that, on the one hand, is served by registers, and then on the other hand is served by local DDR memory. That is when the register content is spilled to DDR memory. So then on a block level, where all threads in the block have access to, is the per block shared memory. So and then eventually, when we have the whole compute grid, then the memory region that is relevant on this level is the global memory, or the VRAM or DDR3 memory. So let's now go over the various memory regions in a bit more detail. So in the first memory type that is of interest is register memory. And we actually already talked a lot about registers and their relevance for GPU architectures, and in particular that local thread state goes into and stays resident in registers, which allows this fast way of performing context switches between threads and between warps that are inactive and that allow the GPU to high latency. And in order to make that work, we actually need many registers and we need huge register files. And for that reason, quite a bit of on-chip memory is actually devoted to registers. Like what that can amount to is actually remarkable. Like for the Tesla P100 GPU, like a couple of years ago, I actually picked out some numbers what the register count would amount to, and I found out that across all shader cores and all shader multiprocessors, the overall memory that goes into registers is actually over 14 megabytes. Like this is actually quite a bit. And then I compared that to the most efficient CPU at that time, which was a 28-core Skylake processor. And then I had to extrapolate a bit, like I could find out how many registers this architecture actually used, but it's not documented if those are 256-bit registers or 512-bit registers. Like, as the architecture, if I remember correctly, supported AVX and not the AVX 512 SIMD instruction set architecture, so it was a bit opaque what the actual size of those registers were. So, and I just estimated an upper bound for the actual register memory, and so I came up with a maximum of 22 kilobytes of memory registers. So they're actually like 3 orders of magnitude between register memory size on the CPU and register size on the GPU. So all this is quite essential, and how the warp scheduler makes use of those registers we actually talked a lot about, and this is actually quite essential to the overall execution model of the GPU. So as said, the state is and stays resident in registers, and that allows for those fast context switches. And when we're talking about register allocation, this is actually already a hard problem when done on the CPU, like on an ordinary processor. Like when we discuss modular scheduling in part 1 of the lecture, those are the typical solutions to the optimization problem that we're talking about here, where register allocation to the program is determined. But when we now take warps and multiple threads, and actually many cores that those multiple threads are executed on into account, that optimization problem actually becomes so much harder. So, and as this optimization problem is so hard, it actually requires manual input from the kernel's developer. So when we program a kernel, like a GPU program that is executed simultaneously by multiple threads, then the kernel's instructions actually determine how many registers the kernel will eventually use. And then we will try to optimize for that, like we will try to keep the overall register usage low. And then at some point, when we cannot optimize anymore, then we will try to figure out what the optimal block size is, given certain properties of the architecture that we're optimizing for, like for instance the compute capability or the shared memory size. And then, based on the register usage of the kernel, we will try to figure out what the best block size is for the warp scheduler to be able to optimally schedule the block on the shading multiprocessors. And the block size will determine how many warps can actually be scheduled at once when processing that block. And there's a tool that we can use to determine the optimal block size. And the tool is just an Excel sheet, and it's called the occupancy calculator. So, and I would propose that we actually have a quick look at the occupancy calculator. Like, this is it. It is just an Excel sheet that can be found in the tools directory of your CUDA installation. And the Excel sheet allows you to enter certain parameters, like for instance, you can edit the compute capability of your device. And as you can see here, whenever I edit something, then also other parameters change in the Excel sheet, like for instance, like the shared memory size that I can enter here. And then you can also set other parameters, like for instance, the number of registers that each thread in your program uses. And whenever I edit such things, you can see that those three graphs change. And the three graphs basically tell you what the occupancy would be, like how efficient your device works whenever you choose a certain block size, whenever you choose a certain number of registers, that is when you're able to optimize your program more and then use fewer registers, or when you can bring shared memory size down. And that would eventually allow you to figure out, given a certain number of registers, how big your blocks should be. And it also allows you to run certain sensitivity analysis, so in order to figure out what would happen if you were able to bring the register count down or if you were able to use fewer shared memory. Here, the occupancy calculator is definitely a tool that you should play around with, and it's just located in your tools directory of the CUDA installation. And you can play a bit with it and try to flip some switches in there and see what changes. And one thing that's important to note here is that the occupancy calculator computes the GPU's occupancy based on a static code analysis. That is, you would use the occupancy calculator to choose a optimal block size, and you would do that based on register count, which on the one hand makes sense. But then on the other hand, you would usually also choose a certain block size based on the control flow in your program. Because you can easily imagine that the block size also influences the way that the GPU can hide latency. I mean, just imagine that you have a block and a single thread in that block takes extraordinarily long. Like there is a loop that the thread executes, and that single thread executes the loop many, many times, while all the other threads in the grid execute the loop only once, or maybe not at all. So this single thread in the grid would basically block the whole execution. And with a finer tile size, with smaller blocks or tiles, the GPU would be able to hide latency better by basically having more work to do from those tiles where there are single threads in there that have those extraordinarily high loop counts. So the occupancy calculator takes a static code analysis into account, and the static code analysis will tell us how many registers the kernel uses. But there are also other considerations that are relevant here and that people should take into account when they decide for the optimal block size. And part of this actually also requires the user to profile their program and run it with actual real-world data. And this is also one of the reasons why the CUDA runtime doesn't automatically compute the optimal block size for the user and just uses that, and instead allows the user to override this parameter. So I think that we have a relatively fair understanding of register memory now and of its relevance to the GPU execution mode. And from there, let's quickly go through the other memory types. And the next memory type that we're quickly going to discuss is shared memory. And this is just an overview of shared memory, and we will later also see an example where shared memory is actually used, where you should be able to get a better and more practical sense of what's going on with this special type of memory. But for the time being, suffice it to say that shared memory is a on-chip memory region, and it's quite similar to L1. And we already discussed that on modern architectures, the L1 and the shared memory are usually very close by, if not, I mean, we don't know that, but if not even the same region of the chip, that they're actually not distinct regions of the chip, but that they're rather one single region, and then you can devote certain bytes to be an L1 cache and certain bytes to be a shared memory. Nevertheless, the shared memory is addressable from within the threads. And however, when we allocate shared memory, and we will also see that in an example later, we always have to do that from the host. Like the host will actually allocate the shared memory region, or we might even do so at compile time so that the shared memory that is available to the threads in the block is static. And whenever we access shared memory from within the threads in a group or in a block, we have to synchronize those accesses. The memory access latency of shared memory is relatively low, like on the order of like 30 to 90 clock cycles, depending on the GPU architecture that you're currently using. Like, this is pretty fast, and this is actually also the order of memory access latency for L1 on GPUs. And in comparison to CPUs, however, where we would have like a 4 to 5 clock cycles latency, the latency is again relatively high. So again, we have this fast on-chip memory, and the on-chip memory behaves like an L1 cache, and again, we see that there are certain characteristics, in particular relatively high latency, that is quite typical to GPUs when compared to CPUs. And on the other hand, we usually also have very high bandwidth on the other hand. And that brings us to the discussion of so-called global memory. And global memory is basically just DDR memory. That is, this is a memory region that is not on board of the chip, but instead is attached via the board and via an interconnect to the GPU. And GPU DDR memory traditionally has this characteristic that the bandwidth is extraordinarily high, while at the same time we have very high latency, like a latency of 200 to 800 clock cycles, where we on a CPU would see well below 100 clock cycles actually. So once again, it is important that whenever we access memory, that we do so in a way that we like fetch a bunch of items at once. So we have to make sure that mechanisms such as prefetching and that caches in general are used effectively. And this is even more important on GPUs than it is on CPUs actually, because of the very high latency when we perform those accesses. And on the other hand, as we have those relatively high latencies, we on the other hand have this architecture that is quite effective at hiding latency. Like when we have our very fast context switches and when we have warps that can, while they're idling, that can be set to inactive, and the context switch from active to inactive and then back to active is very fast because the threads are resident in registers, so their state is resident in registers. All that is designed around very high memory access latencies. And that on the other hand also means that we have to design our programs in a way that there's a tendency to have enough compute and enough work to do whenever we perform those high latency memory accesses. So global memory has certain characteristics, like for instance, that is quite sensitive to bank conflicts, and this also depends a bit on the architecture that you're on. But in particular, you have to make sure that your memory addresses are aligned sufficiently so that you don't run into bank conflicts. And when you, for instance, use CUDA, you will see that there are certain types, like for instance, vector types or certain floating point types, and those types have a natural alignment that helps a lot with memory address coalescing. So then there are a number of special memory types, like for instance texture memory. And texture memory is just a dedicated memory that is optimized for spatial locality, basically. So it's optimized for read accesses as opposed to write accesses. And in particular, it is optimized in a way that accesses to spatially neighboring addresses are quite efficient. Like the specifics and implementation details are not known for those architectures, but we had a very early exercise where we discussed z-order Morton curves and where we saw that this could result in a cache optimization. And it is conceivable that texture memory is implemented in a very similar way, so that the way that texture memory is accessed uses very similar mechanics. Like those are implementation details, we actually don't see what's going on. And as a matter of fact, texture memory is actually not addressable. Like we will never obtain a pointer to texture memory. And this is of course deliberate. Like the way that texture memory is optimized is usually a well-kept secret by the vendors. The vendors will usually try to not leak the specifics of their texture memory implementation and of how texture addresses are computed from 2D or 3D texture coordinate, because this pretty much determines how fast their GPUs actually are. So, and texture memory also has certain other properties, as for example bounce checks, and those are the very same bounce checks that we also discussed in the graphics lectures, where the API helps with texture accesses that go beyond the borders of the actual texture. Like when we access a memory address beyond array boundaries, that usually results in some type of memory access violation. So on a CPU, we would have the operating system intervening, and on the GPU we would just access some memory that might belong to another program, and then eventually we would see erroneous behavior. And with GPU textures, accesses beyond boundaries are actually allowable, and the behavior is defined, and there are usually a couple of different behaviors that can be configured. Like, for instance, that texture coordinates are clamped. So, for instance, if we have a texture coordinate that is negative, then we might clamp it to 0. And there are other behaviors that can be configured, and they are well defined, as opposed to with global memory accesses to global arrays. So one thing that is quite interesting is that texture memory up to the Kepler architecture, which was like around 2012, 2013, there was only a constant number of textures that you could actually have with the CUDA API, and this constant number of textures was proportional to the number of texture units that the architecture exposed. And since the Kepler architecture, there's an extension that is called bindless textures, which also became available with the graphics APIs such as OpenGL or DirectX. And the bindless texture extension allows us to have as many textures as we want. Like, there is a certain limit, but the limit is high enough for us so that we don't have to care. And therefore, things are much simpler nowadays, where we don't have to take care of when we create a texture that we have to bind it to a texture unit, and then we have to make sure that the texture is available on the very texture unit that is currently active. So the next type of memory that is relevant to us is so-called constant memory, and as the name already says, this memory is read-only, and there is usually a small amount of constant memory devoted to each shading multiprocessor. And the implementation of this is actually quite different than the constant memory that is available to CPU programs, where you just have a dedicated memory region where all the real constants go, and then all the threads have access to the single memory region, and there is a dedicated initialization model on the CPU for that. And constant memory is different in that this type of implementation, where you have a single global memory region, just doesn't scale very well. So instead, the constant memory is, on the one hand, it is distributed, but from an application point of view, this is not exposed. So the application basically just allocates this constant memory region on the host and then copies data to that memory region. And on the device, that data is on the one hand distributed, so that each of the SMs has a copy of that memory region. And then, when there are accesses, we have one thread accessing that memory region, and then broadcasting the constant memory to all the threads that also access the constant data items. And this is important to keep in mind when you use this type of memory and when you optimize for constant memory usages. So you will usually try to keep your constant memory data items relatively small because of those broadcasts. And then you will also try to make sure that all threads actually access the same memory address, so that those broadcasts can become a bottleneck. So in a typical use case for constant memory would, for example, be when you're writing a 3D renderer, maybe a ray tracer, and then you might maybe store the camera matrices in constant memory because they only change on a per frame basis. And there are actually only a couple of floats, like they would manifest as 2 or maybe only 1 4x4 matrix. So this would be a very typical use case where people would use constant memory on the GPU and with CUDA. So this was all but a brief overview of the CUDA memory model. And you can see that the memory model is actually quite heterogeneous. So you have lots of types of memory that are exposed by CUDA that you usually wouldn't see exposed on a typical CPU architecture, for example. And as said, this was just an overview, and we will see examples in the remainder of the part of the lecture on CUDA, where we in particular will talk about shared memory and global memory. So for the more important memory regions that people use on a day-to-day basis, we will also see examples, and those examples will help you to better understand what those memory regions are there for and how they are typically used. And for now, it's important to note that the memory model is quite heterogeneous and that there are those different types of memory that behave in such different ways and that are used in such different ways. And that should give us enough understanding for now of how the CUDA memory model works actually. So, and with this discussion of the CUDA memory model, we're also closing today's session. So today we're mostly trying to get an overview of the CUDA programming model, and in the next session, next week, we will see more concrete examples of how CUDA can actually be used in order to write GPGPU programs. See you then.